is based on a real site, involve the injection of strong bases to raise the pH of the groundwater and precipitate or recomplex the trace elements of concern to the oxide surfaces. So the injection scenario, this was a pilot test, involved a fixed release duration of about 90 days. This was at 2 gallons per minute into 2 wells. And the wells received either a calcium hydroxide or a magnesium hydroxide slurry. And the slurry was represented basically a mixture of these chemicals with background groundwater. This was all mixed together prior to injection into the aquifer. If you look at the figure on the right, it shows the locations of the 2 injection wells. And again, one of the wells received a calcium hydroxide slurry and the other received a magnesium hydroxide slurry. As we'll see, these 2 different reagents impart slightly different effects on the water chemistry. So that was one of the things we wanted to look at. There are also cost differences associated with these 2 reagents. So that was a second issue to look at in terms of comparing their efficacy to one another. This is basically what we're showing here are simulated results at the end of the pilot test period after the reagents had been injected. Again, what we have here are 10 years of initial conditions to set up the model, as we had discussed in some earlier slides. 90 days of injection of the reagents, the respective reagents, into the 2 wells. And then we have another 30 days or so to look at conditions at the end of the injection period. So what you can see here in both of these plots, iron is shown on the left and aluminum is shown on the right. We have zones where both the iron and aluminum concentrations are reduced or depleted in the immediate vicinity of the 2 injection wells. So again, no surprise here. The pH goes up at both of these locations, and iron and aluminum hydroxides precipitate out of solution. Move on to some of the trace elements. Again, chromium, arsenic, and nickel, and we see the same sorts of results. The trace elements are removed locally around the 2 injection wells because of the increase in pH. Primarily what happens here are these 3 trace elements are adsorbed onto, again, iron and aluminum hydroxides that precipitate near the injection wells. This is where the difference can come in between using either calcium or magnesium hydroxides as reagents. And these are basically the masses of different mineral precipitates that FAST predicted we would expect to find in association with the well locations. Iron hydroxide is shown on the left, calcium carbonate is shown in the middle figure, and gypsum, calcium sulfate, is shown on the right. So moving from left to right, you can see there's very little difference in the distribution of iron hydroxide around the 2 injection wells. Again, elevated pH conditions, you precipitate out iron hydroxide. They're both looking pretty similar. When you look at the calcium carbonate distribution, calcite, in the middle figure, you can see you're seeing basically a little bit more calcite is precipitating around the injection well to the north. That well contained the calcium hydroxide reagent. The well to the south contained the magnesium hydroxide reagent. So this is pretty straightforward. You're putting more calcium in solution in the northern well, and so you're getting a little bit more calcite precipitation. The main concern for this particular application was precipitation of gypsum, which is shown on the right. There is quite a bit of sulfate present in this water from the sulfuric acid releases over the years. And here we're injecting lots of calcium in the northern well. So you combine those 2 together and you get the precipitation of gypsum, which does not really depend on the pH of the aquifer. It just depends on both calcium and sulfate being present in high concentrations. And it turned out that our FAST simulation was suggesting that large amounts of gypsum could potentially precipitate around the calcium hydroxide reagent injection well, to the point where clogging of the aquifer material and substantially reduced permeability were concerns. And so this information was used to help ultimately select the most suitable reagent for this particular site, which turned out to be magnesium hydroxide. So that's it for this particular example, and this brings us to the end of today's webinar. So we have an opportunity here for folks to ask any questions, and again, you can use the chat feature for this. And I would be happy to discuss some of this. I know we've thrown out a lot of information today, and again, this material will be available as a video file that you can take a look at afterwards if you want to review it. And I will once again I will distribute the slides from today's webinar and the associated FAST input files for you to try this out on your own. So there's one question here about whether or not there is a GUI available for FAST. Yes, there is. If you go to the FAST website, this is a public domain software that's provided through the U.S. Geological Survey, and I will send out a link when I email the material out again today. There is a particular GUI that's called FAST for Windows, and it basically allows you to do what GUIs would do for, let's say, ModFlow. You get to draw out the model domain, set up the grid, draw where you have various sorts of boundary conditions present and features such as rivers, specified head, leaky boundary conditions, heterogeneities in the aquifer, hydraulic conductivity, and so forth. It's all spelled out. I elected not to use FAST for Windows in the introduction material for the class because sometimes using GUIs, I mean, they're helpful on one hand to allow you to quickly and sort of visually set up a problem. But I think it's useful to understand the structure of the underlying input files as well. Again, these are relatively simple keyword block oriented text input files to sort of develop familiarity and expertise with FAST. I find it helpful to sort of look through the text-based input files and kind of play around with them and see what sort of features are there. Once you have some comfort with what is being set up, at least this is my personal view, then it's a little easier to move on to a GUI and sort of set things up in production mode. But I will send out the link for FAST for Windows when I email out the class materials today. So you are welcome to have a look at that. Any other questions from anybody? It looks like that's it for today. I thank you all for oh, we have another question. So why is the spatial distribution of the simulation results has been represented using XX coordinates and not XY? Let's see, if you're referring to the, okay, we've had two different sets of two-dimensional simulation results shown in today's webinar. The first one that I introduced, which was a follow-up to the 1D copper supergene enrichment simulation, was a two-dimensional simulation that was in cross-sectional view. So that would basically be the coordinates for that were really XZ. The Z, of course, being the vertical direction, and X just being the sort of cross-sectional direction for that example. The second two-dimensional example was really looking at an aquifer in plan view. The coordinates should be XY. The XX here, that may have been a possible mislabel on the, yes, actually I can see that now. I'm sorry, that is a bit of a mislabel on that on the plot. It should say XY. Y would be the vertical axis in the results, and X would be the horizontal axis. Thanks for catching that. That's a labeling error on my part. Any other questions? Okay, I'll pause just for a few more seconds to see if anybody else has anything else to add, and then otherwise we will conclude, and I will speak to all of you again next Wednesday, and we'll be talking about bringing Python scripting into some of our simulations to help set up some more sophisticated freq-C models, as well as setting up some more sophisticated FAST models, including heterogeneities and reaction kinetics in that case. So thank you very much. And I hope the rest of you, I hope you all have enjoy the rest of your day. Thank you.